One way to deal with the gap that exists between theory and practice is to completely forego of theory. And let's say we just focus on experiments. We just focus on the running time. For example, you just implemented the algorithm, you implement it. If it's fast enough, then you're happy. If it's not fast enough, you implement something else, you just change something, and so on. And insultingly, there's a quote insultingly summarizes this approach from Garrett. I really like it. It says, I implemented my fancy algorithm and ran it on this big input I found on the internet. It took 87.32 seconds to run the program. So this approach is somewhat useful. It gives you some information. It gives you a fact, right? It gives you a fact that on your machine and on this input, your algorithm took this much time to run. Okay? But the thing is, such things are not easily generalizable. If you then take this algorithm and run it on a different machine or another input, you might not get the same result, you might get a different result, and you might have no idea how to relate the results that you get. In other words, it does not give you that much information, okay, even though it's a kind of a precise and very empirical approach to do things. Algorithm engineering tries to be somewhat in between. So it is a detailed study of algorithms with an emphasis on testing and execution. So testing and execution does not exist in theory, right? We just use pen and pencil or pen and paper to analyze algorithms. But it also has a theory in it, which does not exist in the empirical approach. So we're taking some part of the empirical approach and part of the theory. We try to isolate and control for the influencing parameters, and we try to build models, and we try to build a theory that is tried to predict more comprehensively how algorithms behave on machines. And all of this is to bridge the gap between theory and practice. If you could do that, then we have something of value. Because the main thing about theory is that it's a general statement. Once you say that quicksort, for example, has n log n running time, that's a very general statement that applies to any quicksort algorithm, however you implement it, on any machine and on any input. Okay? And with algorithm engineering, we can do something like that. If we can build very detailed models, and if we can be able to verify that the models are realistic, then maybe we can make statements that can be generalized from one machine to another machine and from one input to another input. So that is the main idea of algorithm engineering. So the algorithm engineering, in fact, can be applied in many different levels. So there's this spectrum of instantiation that's from a textbook that I will link on the course page. And here we can talk about an algorithm in many different levels of abstraction. So we have an abstract description algorithm. So this is what we think of algorithm in theory. But there's also a program, a source code that is written by someone, implemented by someone in some high-level language. So that's also another instance of an algorithm, and those two things might not be the same. If you have ever implemented a theoretical algorithm, you will know that typically there are instances where it is not clear how you should implement, and you have many different implementational choices, and some of them makes actually a difference. Once you have a program, how you compile it or link it could influence how the code runs. Compilers are now very complex. They have many different optimization parameters or options, and that can also change the behavior of your program. And finally, once you have a process that is running, the environment that the process is running into could have an impact on it as well. The hardware and all these things also make a difference. So when we think about algorithm engineering, we could think, or we could target any of these points in the development of, or in the process of going from an abstract description to a running code. And inspired by this, she also defines this design hierarchy where the algorithm engineering could be useful. I'm not going to go into these details. There's also another view of algorithm engineering. So this is by Peter Sanders. So in a paper called Algorithm Engineering, an Attempt at Definition, he tries to define algorithm engineering as a scientific process inspired by Popper's scientific method. So if you know a little bit about history of science or philosophy of science, you probably have heard the name Popper. But basically, the idea here is that you should have a falsifiable hypothesis that's at the center of everything. This falsifiable hypothesis could be anything that relates to the running time or the behavior of your algorithm in an environment or given a particular input. And then around this hypothesis, we try to do some analysis. We try to follow scientific method. We run experiments, we design new things, we analyze them, we implement, and we get the experiments again, and then we run, we analyze, and etc. We follow a cycle. And in that paper, Peter Sanders tries to relate all of these different components of this picture to various parts of algorithm engineering. I'm not going to again go into the detail, but here the interesting thing is the formulation of algorithm engineering as a scientific process, because typically we do not think of algorithm design as a scientific process, right? We come up with an algorithm, we analyze it, it's done. It's more like mathematics, the way we do things. But here the emphasis is on scientific process, which implies that you should have a hypothesis that can't be falsified, and you should design and run your experiments with respect to this hypothesis. And once you give some evidence for the hypothesis, this is then that you can now have some generalization, because that's how, let's say, science works. That once you have a theory of how your algorithm behaves, then you can use your theory to predict how your algorithm behaves in another machine or on another input.